ladies and gentlemen. I'm Althea Mackenzie. Welcome to the summary of the third in our Cadmium Talk series. We've had 3 excellent presentations in the series thus far, and we're happy to bring you a synopsis of Webinar 3, which was held on Tuesday, November 28, 2023. This project falls under the auspices of the Inter-American Institute for Cooperation on Agriculture, ICA, and the International Cocoa Organization, ICCO. The project is aptly named Improving Capacity Building and Knowledge Sharing to support the management of cadmium levels in cocoa in Latin America and the Caribbean for export to the European region. Here's Dr. Elizabeth Johnson, the project lead, to give you her welcome to the proceedings.
So let me take this opportunity to say good morning to you all, to welcome you to this session. We are really proud and pleased to have you join us today. And so we will continue to try and bring as much information that we can bring to you in a packaged form.
The first presenter was Dekeyrel, PhD student at the Division of Soil and Water Management at the Catholic University of Leuven in Belgium. His topic was quality assurance in laboratory testing for CD in cacao soil and tissue samples. Among the interesting information he shared was the use of ring tests.
So first, what is a ring test? A ring test is a quite easy concept. In a ring test, a certain laboratory, in this case it was our laboratory in Belgium, will make one or multiple samples. In this case, we made some cacao samples and some soil samples. And that laboratory will distribute all these samples to the participating laboratories. So every laboratory that is participating in the ring test will get the same sample or the same set of samples, which they then have to analyze and report concentrations of course. And all of the results that are reported by each laboratory are again collected by the organizing lab, by our lab. And from all of the results that the laboratories gave us, we make first a general report and second a lab certificate. So the general report is less important for the customers, but it's more scientific and more important for the labs. And it just summarizes all the results, how everyone performed, the statistics behind it and everything. And then more importantly is the lab certificate. So every lab that participated received a certificate, which I will show an example of later. And on this certificate, they can see the results that they reported, the certified results or the results of the samples that they should have reported, and then some kind of scoring system to see how well they performed in the lab, in the test.
In making the point about the importance of high laboratory testing standards, Yassa also speaks about and gives an example of the lab certificate.
Okay, so this is what the lab certificate looks like that every laboratory got when participating in this ring test. So let's zoom in a little bit on the most important and interesting part, which is this graph right here. This is not a real certificate. All the numbers are made up just to protect everyone involved. But here we can see what the important things are and what you should look at. So first, we see that there were 4 samples in this simulated ring test. And in the second column, we see the reported concentrations. So the concentrations that the laboratory reported for each sample when analyzing the cadmium, of course, in that sample. And in the third column, we see the consensus value. So this is approximately the cadmium concentration that is in that sample. So of course, the reported concentration should be very close or the same as the consensus value. Then in the last column, we see the Z-score again. So the Z-score was also what I showed in the graph in the last slide. And I told you that the acceptable Z-scores were between -2 and 2, all right? So again, this is the consensus value. So this is the reference. So the reported cadmium concentration should be close to this value. And then here we see the Z-score with acceptable range between -2 and 2.
YASA notes that certification and accountability are key in providing high quality assurance standards in the cocoa industry, particularly in reference to the reduction of cadmium levels. He says training of laboratory personnel is a key component of this undertaking. He also addressed the use of reference materials in sampling.
So now we are working with all the laboratories that participated in these ring tests on two main aspects. So first of all, we of course want to improve the quality of the results. But second of all, which is also very, very important, we want to improve the quality control, because some of the laboratories didn't have any control whatsoever. So they were not, of course, they didn't know that some of their results were very bad or very, very unacceptable. So we want to improve checking the quality of your measurement and also reporting this to customers. So customers like you can see how good the measurement actually was. And this brings me to the second point, checking the quality of a measurement. So this is more for the customer. Laboratories and people working in a laboratory should already know this. But this is a very, very important aspect. And here I will talk about first the different types of reference materials, and then second about the most important one, the solid reference materials. So a reference material is something we can use to check the quality of a measurement. Let's see here. The reference materials are materials with known concentrations of certain elements, for example, cadmium. So they have certificates, and on these certificates, we have the exact concentration of certain elements in that sample. So we include these samples in a measurement to check the quality of that measurement, because we exactly know, for example, the cadmium concentration, and then we look at our result, at our measurement, and if that result is close to the certified value, then we know that it was a good measurement, and the other results of the unknown samples can also be trusted. And in this regard, we have two main categories of reference materials. We have the solid ones and then the liquid ones. Now, why did I say that the solid ones are more important or more useful? This is because the solid reference materials go through the whole process. So the liquid reference materials, they are already a liquid and they just get put into the equipment and they get analyzed. However, the solid reference materials are still a solid, like your samples that you send to the laboratory. They first have to be digested, they have to be diluted, and only then can they be measured. So they go through the whole process. So this is a category that is a little bit more important and can tell you more about the measurement as a whole. And how do we quantify how good this material was measured or analyzed? We do this with the recovery. So very easy. The recovery of a certified solid reference material is the measured concentration divided by the certified concentration that we, of course, see on the certificate as a percentage. Of course, we want this number to be as close to 100% as possible. Because if we have 100%, this means that the measured concentration by the laboratory is exactly the same as the certified concentration. However, 100% exactly is, of course, very difficult to obtain. So in our lab, this does differ from lab to lab, but in our lab, we want to aim at a range of 90 to 110%. So if, the recovery of a certain sample, reference sample for a certain element, of course, is between 90 and 110%, then we say, okay, this element was analyzed very well.
An exciting part of Yasser's presentation focused on the use of the Emax machine, which uses the XRF technique, and it was an instant hit with participants in the webinar.
So this is what the machine looks like. So I mentioned the Emax, which is optimized for heavy metals like cadmium, but there's also a JP500, which is more optimized for lighter elements like the plant nutrients, macro and micronutrients. However, this is a little bit less special. There's already multiple machines that use XRF for these elements. However, XRF has never been very good at measuring the low concentration heavy metals like cadmium. And this is where the Emax shines. It is optimized in the machine itself. All the parameters are optimized for the analysis of these heavy metals in low concentrations. And it is the first time that an XRF machine can really measure the very low cadmium concentrations very well. Okay, so let's have a look at the results that we got with it so far. So in this graph, you see on the y-axis, the cadmium concentration measured by the Emax. And on the x-axis, the cadmium concentration measured by ICP-MS, which is the conventional method, very expensive, very accurate. So this is a very reliable thing to compare the results of the Emax to. And here we see that all the results are approximately on the 1-1 line. We also see this in the equation of the graph. So 1.04 is the slope, which is very close to 1. And the R-square is also a parameter for how well the fit is. So we do see that all of the samples are very close to the 1-1 line, which means that the results of the Emax are very similar to the results of the ICP-MS. And we tested this for multiple sample matrices, but most importantly, we have, of course, the cacao and the soil samples, but also we tested leaf samples. So now let's zoom in a little bit on the more relevant range of 0 to 2 milligrams per kilogram, which brings us to this graph. And we still see, of course, that the results are very, very close to the 1-1 line, and that the Emax results then are very similar to the ICP-MS results. So this is very, very new and very, very good results. I cannot stress enough how well the machine performed here. So this is unprecedented, and we were really amazed by this. So this is, of course, for cadmium. For some of the other elements, the results are less good because the Emax is optimized for cadmium. But to analyze cadmium, it is very, very suited. And we were very surprised, even at low concentrations. Then we also have another graph, which I will not dwell on too much. But here we see the variability between replicates of a sample in function of the cadmium concentration in that sample. So we do see that the variability goes up if we go to low concentrations, especially for the soil samples, which are these plus signs. So we do see that at low concentrations, we have to be a little bit more careful because the variation can really increase a lot. But in general, if we look at the previous graph, we do see that even at low concentrations, the machine performs very well. Maybe we have to measure a little bit more samples or a little bit longer. But as you will see later, the measurements are so cheap that it doesn't really matter too much. Okay, then to end, I will want to talk about some advantages, but also some disadvantages of this new technique and this new machine. So first, like I already showed you, the cadmium results are comparable to conventional methods, which is the first time ever that the results are that good. So this is really nice. And it can also, of course, analyze other heavy metals and nutrients, sometimes with less accuracy. So for now, mostly cadmium is analyzed very well. With arsenic and lead, we have a little bit more problems. Also because the arsenic and lead concentrations in cacao are often way, way lower than cadmium. And of course, for the easier elements like the nutrients, it can also perform well, but cadmium is a little bit more important for us right now. Then it is also faster. So here in this table, I just summarized how long it would approximately take to analyze 100 samples. And we see with the Emacs, you only have to do the measurement. You can prepare the samples while measuring, because a measurement takes a couple of minutes and preparing the samples is very fast. So the bottleneck is the measurement and not the preparation of the measurement of the samples. So we see that 100 samples would take 2 days. And for ICP, because you have to weigh the samples, you have to digest the samples, you have to dilute, you have to do a lot of sample preparation, the total will be approximately 5 days. And then with ICP, there is also a much longer waiting period between the digestion step and the measurement. Again, with the Emacs, you don't have to do the digestion step. There is only the measurement. So in total, it will be way, way faster. Then it is also cheaper. So I calculated only based on consumable materials that for one sample, the conventional method should be around $9 per sample. Probably if you send it to a laboratory, it will be more expensive than $9 per sample because you also need insurance costs, working hours, and so on. And for an Emacs, it will be around $0.5 per sample because there's almost no consumable. The only consumable is one plastic sheet that you use to cover the sample. And these sheets are sold now for 50 cents per sheet, and that is why I put 50 cents. Apart from this plastic sheet, there is no other consumable. Only electricity, of course, for the machine, but nothing else. Only the plastic sheet. It is much, much easier. So you can easily train someone to work with the Emacs in half a day or a day max. As for the ICP or the other conventional methods, it can take a couple of weeks to really get accustomed to the technique. So the Emacs is very, very easy. The sample preparation is easy, and the measurement is even easier because you just have to press start and it measures the cadmium concentration for you. So much easier, much cheaper, and much faster. Then the last one is that it is portable. So it is not recommended to take the machine into the field, but you can easily carry it from lab to lab, from room to room, no problem. It is not recommended to take it into the field because all the movement and the dust can maybe damage the machine. So I would not do it. You could do it if you have a battery, but in general, it's not recommended. And here, the picture is just to show the size of the machine compared to other conventional methods like the ICP-MS, which you see in the background. So you see that the machine is much, much smaller. Then quickly, some disadvantages. So it is unable to measure very light elements like aluminium and so on. This is still a problem. They are trying to find a new optimization for a new machine to do analyze that can analyze lighter elements, but for now it lacks in this aspect. Also, for the soil samples, it is worth noting that it measures the total concentration of elements, and often right now in laboratories, not the total concentration is measured, but the aqua regia digestible concentration. This is not wrong, it is just different. And therefore, some of the soil concentrations only in soil samples may be a little bit different. However, we see for cadmium that the total concentration is very, very, very close to the aqua regia digestible concentration. For other elements like zinc, it may have a bigger difference, but for cadmium, this is not really a problem. And again, it is also not wrong to measure total concentrations. It is just more used right now in research to use the aqua regia digestible concentrations. Then it is still less accurate than conventional methods, especially than the ICP-MS. ICP-MS will always be better because it is just so complicated and so expensive that it will always be a little bit better. But we do see for cadmium that this difference is becoming very, very small and maybe not really as important. And then controlling the quality is a little bit harder because you don't really have those reference samples. You can make a reference sample, but you can always just use the same one. So the quality control is a little bit sketchy in this part. There is quality control possible, and we do know how to check if the machine is working. But with the conventional methods, they have been used for so many years. It's so much more fleshed out. So there's still a lot of research that can be done here. But this is just, it's not a very big disadvantage. It's just for now that the quality control is not that fleshed out yet. And then the results for other elements, like I already said, are not always as good as the conventional methods. For right now, the cadmium results are really, really excellent, but the results like arsenic or lead are a little bit more difficult. So for now, I would only recommend using it for cadmium, which is, of course, why we are here in the cadmium talks. So for the cadmium talks, this is very good news, but for other elements, there is still improvement possible.
Now, having ended on that intriguing note from IASA, it was then time to hear from Ruth Quiroga, environmental engineer with specialization in environmental chemistry from the Industrial University of Santander, Colombia, and Deisy Toloza, a biologist who graduated from the Pedagogical and Technological University of Colombia. The ladies presented on the topic from field sampling to preparation for lab quantification. Ruth Quiroga presented first, and with the presentations being done in Spanish, we invite you to listen to the interpreter as you follow the slides. She emphasized the importance of collecting samples.
Lab analyses are key or are a tool that allow for decision making. In this case, appropriate sampling is key in allowing us to understand the status of cadmium content in our cocoa crops. We need to highlight that this heavy metal, as has been highlighted in all of the previous webinars, is found in the soil and it's transported through various mechanisms towards our plants. We need to keep this in mind because we need to have proper sampling in our crops to ensure a representative sample that allow us to correctly identify the cadmium contents in our crops and in the different matrices that comprise it. Now, what specifically do we need to do in our crops to have truly representative samples that can truly highlight the contents in our crops? Well, in any kind of cocoa crop, we need to first of all identify the topography as far as the area of the crop, the extension of the land, the topography itself, whether we have different types of aspects such as drainage and color. And it's very important to geo-position or geo-reference the locations where we take the samples through GPS. Once we have identified these basic conditions for the crop, we need to prepare the materials according to the matrix in order to obtain the samples. Now, in the case of cacao crops, we can obtain samples from either the soil or the tissue. And through the presentation, we will focus specifically in the tissue because we can have samples of the beans, but also of the leaves. For soil samples, we need a bucket. We need to also highlight that most of the materials that we use for sampling, any kind of cacao farmer has all of these tools at their farm. Now, for the soil, as I mentioned, we will need a bucket, a small garden shovel, a knife, a Ziploc bag, and we also need to collect data related to the sample.
Information was shared about how to collect samples of leaves, tissues, as well as cocoa pods.
Now, in the case of samples of vegetable tissue, I mentioned that one of the matrices are fresh leaves or leaves from the tree directly. To take these samples, what we need to do is to pick, at the very least, 5 trees within the crop area. We can follow one of these patterns here in the shape of a W, Z, or an X. Once we have picked our trees, what we need to make sure is that we take a sample from the third median of the tree between the second and third leaf, and to make sure that the leaves are mature. Now, for the case of another tissue, which can be dry, which can be the pods or the dry and fermented beans, then the sample depends on the goal that we have in mind when sampling. If we want to collect pods, then we may want to assess concentration in a specific variety within our crop, in which case, what we do is we select pods from this variety specifically, keeping in mind that depending on the index of the bean that we have in that variety, and we'll see the availability of the beans that will be extracted to continue with the analysis. In the case of dry and fermented beans, we recommend doing sampling on site where the things are processed at the farm.
The presentation ended with Daisy's focus on the process that takes place when the samples get to the AgroSevilla lab.
This part of the protocol is going to be based on the protocol used at AgroSavia's laboratory. So in this slide, this summarizes of the minimum quantities required for cadmium analysis in each matrix. Once we look at the video, we'll be able to understand this more clearly. But just to take into consideration, in leaves, you need a minimum of 12 leaves for about 50 grams of the matrix. For stems, means for the soil, you need 500 grams if you want to do an cadmium analysis and other analysis for other elements. But if it's only for cadmium, you can use 250 grams. In the case for root, 100 grams. Leaf litter, around 250 grams, which correspond to 5 subsamples, each of 50 grams, which are taken in an area of about a hectare. In the case of dried and fermented beans, 100 grams are required for the analysis. Here, we're going to tell you in very general terms what are the 3 macro processes that entails doing the entire analysis at the lab. So first of all, we need to take into consideration sample reception. This reception means that when the sample arrives to the lab, a code is assigned to it, and this will be its unique identifier from the moment the sample is received to the moment a outcome or result is delivered. So this is how we're going to identify the sample throughout the process. And it's very important. In this part of the reception part, we do a verification to identify the sample. That is to see that the amount of sample is the one that is required to do the analysis, and also for the sample not to have any foreign particles that may be contaminating and affecting the analysis. Now, when dealing with the analysis as such, we're going to take it as in this general process, the matrix for soil, leaves, and leaf litter. So in this part, the first thing we do is to homogenize the sample. And as the name says, the idea is to have a uniform sample for the analysis to move forward. And then the drying is a very important process because it complies with 2 objectives. First, reduce the level of humidity in the sample. According to the literature, one sample has between 70-80% of humidity, and after this drying percentage, it is reduced to 10 to 20% approximately. The other objective of this process is that with the drying, you stop all the metabolic processes that may still be originating in the sample. So this drying process is important because the outcome is expressed in dry weight. So the humidity of a sample will depend on many factors, like the time the sample was taken, the density of solar radiation, wind, etc. So among all the factors, and they may be affecting the outcome of. So that's why we express the outcome or the result in terms of dry. And this is done in temperatures under 60 degrees centigrade, depending on the matrix. The time may be sometime between 48 hours. And if more time is required, you just leave the sample drying for longer. And if it is verified constantly and until we know that the sample is completely dry. Then we have the grinding and the sieving. The grinding is reducing the size of the particles and sieving in separating them. So you use screens from different size screens depending on what wants to be analyzed. Usually it goes from 0 to 0.2 millimeters in the lab, but in the case of heavy metals, we use from 0.05 millimeters. And just to give you another example, if you want to analyze organic carbon, you use a 0.18 millimeter screens for organic carbon. So in this point, you guarantee that the characteristics are kept in the sample to continue with the acid digestion or extraction process. And the idea is that you add acids, oxidative acid, and an external heat source, like a sort of microwave, to extract the metals that want to be analyzed. In this specific case, we're talking about cadmium. And lastly, what we do is the determination and quantification of the metal. And as it was explained in the previous presentation, in the case of Agrosabia's laboratory, we use ICP-MS, which determines the concentration of cadmium in minimum concentrations in the sample.
That was Deisy Toloza sharing information on the rigorous testing process once samples get to the Agrosavia lab. As was pointed out by Yasa in his presentation and endorsed by Ruth and Deisy, testing protocols may vary from one lab to another. However, maintaining high standards is very important in ensuring the integrity of the process. It is clear from the presentations in Webinar 3 that quality control, proper sampling, and rigorous testing are critical planks in seeking to ensure that here in the Caribbean and Latin American region, we are able to keep cadmium levels in cocoa at acceptable levels. It will take all hands on deck. And that is why in our next webinar, we will continue to speak with experts so that together we can develop that narrative of change in some of our agronomic practices that will ultimately lead to making us more competitive in the cocoa and chocolate market worldwide. Until next time, I encourage you to continue to learn more about cadmium levels in cocoa. 400,000 farm families are depending on it. This work is made possible through project grant funding and support provided by the STDF and the 11th EDF of the European Union. From the Cadmium Talks team, I'm Althea Mackenzie.